Hi everyone, here is the part 3 of our chapter 20. We're going to learn a little bit more about delta G note in this section. Okay, delta G note and useful work. Now you guys know this note represent that if the reaction is happening at standard conditions. Delta G is the maximum useful work done by a system during a spontaneous process at constant temperature and pressure. In practice, though, the maximum work is never done. Free energy not used for work is lost to the surroundings as heat. Okay? Delta G is the minimum work that must be done to a system to make a non-spontaneous process occur at constant temperature and pressure. So if you want a non-spontaneous process to make it happen at constant temperature and pressure, delta G is the minimum work that must be done. We know a reaction at equilibrium, delta G system would be 0 because there is no forward reaction, no backward reaction happening. They are at equilibrium. So at equilibrium, delta G is 0. Can no longer do any work. Okay. Effect of temperature on reaction spontaneity, and we will see some conditions. Spontaneous at all temperatures. Let's see our reaction equation. Delta G system equals delta H system minus T delta S. Under certain conditions, reaction is spontaneous at all temperatures. Let's look at what are those conditions. Reaction is spontaneous at all temperatures if it meets these requirements, meaning if delta H is less than 0. What do you mean by delta H is less than 0? If delta H is less than 0, this term will become negative. Delta H is negative. And delta S greater than 0. If delta S is positive value, that positive times this negative will make it negative. So you have a negative term here. You have a negative delta H value. So negative, two numbers will add up to another negative value. So the spontaneous, if the delta G is less than 0, it would be spontaneous. So the reaction is spontaneous at all temperatures if delta H is greater than 0, if delta H is negative and delta S is positive. Okay, so that will make delta G negative, meaning less than 0 for all temperatures. Reaction would be non-spontaneous at all temperatures if these conditions are met. What are those? If delta H is greater than 0. If delta H greater than 0, meaning this is positive. And delta S less than 0, meaning negative. If delta S is negative, so delta H going to be delta H going to be greater than 0, meaning this term is positive. Delta S less than 0, this is negative, delta S. So this negative and this negative will make it positive. So you have two positive terms to add up. So the delta G then become greater than 0 and there would be non-spontaneous. Delta G greater than 0 for all temperatures if it is a endothermic reaction and delta S also less than 0. Okay. Effect of temperature on reaction spontaneity. Another one would be reaction becomes spontaneous as the temperature increases if delta H greater than 0. Remember our equation would be delta G equals delta H minus T delta S. Reaction becomes spontaneous as the temperature increases if delta H greater than 0, meaning here you have a positive value and delta S also positive. So this is T. Delta S positive. So this positive and this negative will make it negative. And let's say delta H also positive, but the temperature increasing, so the T delta S term will increase and the negative term increases. As the negative amount increases, delta G become spontaneous. Okay. Reaction becomes spontaneous as the temperature decreases. Let's look at it again. Delta G equals delta H minus T delta S. So we are decreasing the temperature. If delta H less than 0, meaning this term is negative, and entropy delta S need to be also less than 0, negative. So this negative and this negative will become positive. So the temperature going down. So the T delta S term become less. Delta H become negative. And the T delta S would become positive, less positive. Since the temperature going down, so the delta G will become spontaneous, less than 0, negative. More negative as the temperature decreases with these conditions. Okay. Determine the effect of temperature on delta G. A key step in the production of sulfuric acid is oxidation of sulfur dioxide to sulfur trioxide. 2 sulfur dioxide with oxygen giving us 2 sulfur trioxide. And for this reaction at 298 Kelvin, delta G negative 141.6, delta H negative 198.4, delta S negative 187.9. Use the data to decide if this reaction is spontaneous at 25 degrees Celsius and predict how delta G will change with increasing temperature. Okay, so we have these values given to us. We note the sign of delta G to see if the reaction is spontaneous. What is the delta G? It is negative, so it is spontaneous, right? And the signs of delta H and delta S to see the effect of temperature. We can then calculate whether or not the reaction is spontaneous at the higher temperature. So the value for delta G is negative, less than 0 at 209. So the reaction is spontaneous, right? Delta S also less than 0, negative. So the term T delta S, since the delta S is negative, this is negative. Negative times negative will make it positive, greater than 0. And this term will become more positive at higher temperatures. This is a positive term, right? What happens as the temperature increases? And delta G therefore will become less negative, because even though delta H is negative, and this term will become positive. So the difference would make it delta G will become less negative and the reaction less spontaneous with increasing temperatures. Okay. And then the part B, assuming delta H and delta S are constant with increasing temperatures, no phase change, is the reaction spontaneous at 900 degrees Celsius. Now we can use equation delta G equals delta H minus T delta S, having the temperature 900 with these given values. Excuse me. We first need to convert 900 Celsius to Kelvin by adding 273.15. And then entropy is given in joules, so we need to convert it to kilojoules. Negative 187.9, 0.1879 kilojoules. So delta G would be delta H, this is the value given, 198.4, minus the temperature times the entropy in kilojoules. So delta G is 22, positive. Delta G is greater than 0. So as the reaction temperature increases, it becomes non-spontaneous. Okay, so at 900 degrees it becomes non-spontaneous. And we also predict the same here. Delta G will become less negative and the reaction less spontaneous with increasing temperature. So at 900 it is non-spontaneous. Finding the temperature at which a reaction becomes spontaneous. At 25 degrees Celsius, 298 Kelvin, the reduction of copper oxide is non-spontaneous. Delta G positive 8.9. Calculate the temperature at which the reaction becomes spontaneous. Okay, we need to calculate the temperature at which delta G crosses over from positive to negative value, right? Because in order for it to become spontaneous, this positive value need to become negative. We set delta G equal to 0. Okay, and then we're going to solve for temperature using the values for delta H and delta S from the text. Remember, delta G equals delta H minus T delta S. So we're going to keep this one to 0. If you make that 0, so then the delta H equals T delta S. Right? So then the temperature would be delta H over delta S. That's what here, delta H over delta S. Delta H was given 58.1, delta S 0.165. So temperature 352 Kelvin. So we kept the delta G to 0. At any temperature above 352 Kelvin, the reaction becomes spontaneous. Okay. Delta G, equilibrium and reaction direction. A reaction proceeds spontaneously to the right if Q, remember the reaction quotient and the equilibrium constant, if Q less than K, it would go in the right direction. If Q is greater than K, then in order to become equilibrium, it should go reverse direction, right? So here Q is less than K, so the reaction will proceed spontaneously to the right. Right? So Q is less than K. So then the Q over K, Q is a small number, K is a bigger number. So it's going to be less than 1. If you have a less than 1 value, if you take a decimal value for ln, Q over K, going to be less than 0. So the delta G also will be less than 0. Okay. A reaction proceeds spontaneously to the left if Q is greater than K. So then the Q over K going to be greater than 1, ln Q over K going to be greater than 0, and delta G would be positive. A reaction is at equilibrium if the Q equals K, Q over K is 1, ln 1 equals 0, and delta G is 0. Delta G, Q and K. We can relate delta G, Q and K with this equation. Delta G equals RT ln Q over K. Delta G equals RT ln Q over K. In other words, since this is a division, we can expand it RT ln Q minus RT ln K. If Q and K are very different, delta G has a very large value. It could be positive or negative. The reaction releases or absorbs a large amount of free energy. If the Q and the K are very different. If Q and the K are nearly the same, delta G has a very small value, could be positive or negative, and the reaction releases or absorbs very little free energy. For standard state conditions, Q equals 1. If Q equals 1, ln 1 would be 0, right? So then the delta G naught would be only negative RT ln K. If Q equals 1, standard state conditions, Q equals 1. If the Q equals 1, this part become 0. So then the delta G would be negative RT ln K, negative RT ln K. A small change in delta G naught causes a large change in K due to their logarithmic relationship. As delta G naught becomes more positive, if this becomes more positive, then the K becomes smaller. If delta G naught becomes more negative, so then the K becomes larger. Meaning delta G naught become more negative, meaning it's a spontaneous reaction. So the equilibrium constant also large for a reaction like that. To calculate delta G for any condition, we can use this equation. Delta G equals delta G naught under standard conditions plus the RT ln Q. Under standard conditions, delta G naught would be negative RT ln K. Okay. Q, K, delta G and reaction spontaneity. So this table summarizes what happens at different Q and K conditions. Q is less than K, so then the Q over K going to be less than 1, ln Q over K going to be less than 0, so the delta G going to be less than 0, meaning it's negative spontaneously to the right. And if Q is greater than K, we talked about this before, delta G going to be greater than 0, this would be spontaneous to the left. If Q equals K, it's at equilibrium. Exploring the relationship between delta G naught and K. Use appendix B to find equilibrium constant K at 298 Kelvin for the following reaction. We are given this reaction. And then use the equilibrium constant to calculate delta G naught at 298 Kelvin for the following reaction. And it is 2HCl giving you hydrogen plus chlorine and K is given. Right, let's look at the first one. Appendix B to find K at 298 Kelvin for the following. We use delta G naught values in appendix B with equation to find delta G naught, and then we use okay, so let's do this one. All right. Solving for delta G naught using delta G naught formation values from the appendix B and equation 20.8. So this is the equation 20.8 where delta G naught equals sum of all the delta G naught values for the products minus the sum of the delta G naught values for the reactants. So 1 mole nitrogen dioxide and the delta G value for that. So these values should be given to you. And that is the product minus the reactants 1 mole nitrogen monoxide times the delta G naught value for the nitrogen monoxide. And then oxygen half mole times the delta G naught value for the oxygen. Yeah, so this is our equation. Products minus the reactants delta G values. So first you calculate the delta G naught. Okay. And then what it's asking is to find K. Okay. So now we're going to relate delta G to the K using this equation. Delta G naught equals minus RT ln K. R is the gas constant, T is the temperature. Okay, so we know the delta G naught, we found it, negative 36. So if you take ln K, that would be delta G naught over RT. Okay, negative delta G naught over RT, and then negative sign is there, and delta G naught is negative 36, and converting it to, this is kilojoules, converting it to joules, and then you divide this by gas constant 8.314 mole joules per moles per Kelvin, and then the temperature 298. So 14.53, that is ln K. ln K 14.53. ln K. So the K would be E 14.53, 2.0 into 10 to the 6. So that is how you would calculate K, equilibrium constant, from the delta G naught using this equation. Okay. And then the question B, use the equilibrium constant to calculate. Now the equilibrium constant is given. You have to calculate the delta G naught. You're going to be using the same equation, but now the opposite is what you're going to find. You are given the equilibrium constant. Now you're going to calculate the delta G naught for this reaction. So you can use again the same equation. K was given to us, delta G naught equals minus RT ln K. This is K ln K. You can get the ln K. Negative R 8.314. Temperature 298. ln K negative 76.9. So when you calculate this, you can find out the delta G naught. Okay. Right. Another question, the oxidation of sulfur dioxide is the key reaction in the manufacture of sulfuric acid. Calculate the equilibrium constant at 298 Kelvin, and we are given delta G naught, negative 141.6 kilojoules per mole of reaction as written. Let's do that first. Okay, so easy again. We know delta G naught, temperature, and the gas constant, so we can calculate K. We use this equation, delta G naught equals negative RT ln K. So the K is going to be exponent negative delta G naught over RT. At 298 Kelvin, negative delta G naught over RT. Delta G was given negative 141.6 kilojoules, converting it to joules, divide by gas constant and the temperature 57.2, and you take the exponent of that, that gives you equilibrium constant. Okay. And then the part B, a container is filled with 0.5 atmosphere sulfur dioxide, 0.01 atmosphere of oxygen, 0.1 atm of sulfur trioxide. These three components kept at 25. In which direction, if any, will the reaction proceed to reach the equilibrium? Now, since we are given these values, we can find out the Q, reaction quotient, right? Products over reactants. Q, calculating the value of Q. Product is sulfur trioxide raised to the power 2 because the coefficient is 2, and the reactant sulfur dioxide and oxygen, and these are the values, partial pressures. So you put that and you can find out the Q. Now the K, because Q, here Q we found 4 and K is a large number, Because Q is less than K, the denominator will decrease and the numerator will increase. So more sulfur trioxide will form until Q equals K. Right? Since it has not reached the equilibrium, so the reaction will proceed to the right. If the reaction proceeds to the right, more sulfur trioxide will form until Q equals K. To reach equilibrium, the reaction has to proceed to the right. In which direction, if any, will the reaction proceed to reach the equilibrium? Right? We found the K from the first calculation, found the Q for this one since it's a large K and Q is less, so reaction has to go forward direction, so sulfur trioxide will increase. So it would go to the right, and then it's asking calculate delta G for the system in part B. Calculate the delta G for the system. Now we have Q and K both, so we can use that. Okay, we can use this equation actually. Delta G at 298, equation would be delta G naught standard Gibbs free energy change plus the RT, L and Q. We found delta G naught negative 141.6. It was given to us negative 141.6 kilojoules plus the R gas constant, the temperature, and L and Q. Q was 4, which is found. So when you solve for this one, it will give us the delta G at this time, negative 138.2. It's spontaneous. Since Q is less than K, reaction is proceeding to the right direction. So the delta J is negative 138.2.